Okay, let's unpack this. Imagine you've built this incredibly delicate, vibrating structure, maybe like a crystal or a perfectly tuned instrument. Now, you need to know if its internal harmony is still perfect, if it hasn't been subtly distorted by tiny vibrations from the outside world.
Right, the environmental noise.
But the catch is, if you try to measure its harmony directly, if you touch it, you'll probably mess it up or even shatter it.
Yeah.
And that's basically the core headache in quantum computing, right? Entangled states, those perfectly synchronized quantum systems, are incredibly fragile.
Extremely. Environmental noise causes them to drift. They lose that vital quantum connection.
And the standard way we measure quantum states usually destroys the very entanglement you wanted to check on, or maybe even use.
That's the central dilemma they're facing. This loss of quantum properties is often called decoherence, or, in the context of this paper, drift.
Drift.
Detecting that drift, ideally as it's happening without disturbing the system, is absolutely essential if we want to build reliable quantum computers using entangled qubits.
Because traditional measurement, it forces the quantum state to collapse into a single outcome.
Which is inherently destructive to the superposition and entanglement.
Yeah.
And that's where we're taking a deep dive today into a fascinating piece of source material. A research paper that tackles this problem from a truly surprising angle.
A really different perspective.
It proposes a way to check on that fragile quantum harmony without breaking it by drawing a connection between quantum mechanics and, well, the fundamental structure of numbers. Arithmetic, really.
What's really exciting here is that this paper introduces a completely new, measurement-free in the destructive sense, protocol to detect drift in entangled systems.
Okay.
Our mission in this deep dive is to explore their core ideas, how they use the arithmetic fingerprint of quantum states to spot errors.
Arithmetic fingerprint, I like that.
Yeah, and a surprising related discovery about how these systems behave. Think of this as a shortcut, maybe, to understanding how looking at the mathematical DNA of quantum states might offer a backdoor to non-destructive monitoring. And the foundation they build on is a framework they call spectral quantum mechanics, or SQM.
That's the one.
It's this idea that quantum states have a much deeper inherent link to the prime factors of numbers than we previously understood, placing them in what they term a prime logarithmic spectral space, which sounds pretty complex.
It does sound like a mouthful.
Yeah.
But let's start by trying to make sense of that first concept. The arithmetic of quantum states, as this paper describes it. SQM isn't just a minor tweak to quantum theory. The source material presents it as an arithmetic reformulation.
Okay, so how do you connect a quantum state to arithmetic, like practically?
Well, the idea is surprisingly direct at the foundational level. In SQM, each standard computational basis state, like the state representing the number n.
Okay, like 0, 1a, 2, and so on.
Right, each of those is mapped directly to a vector based on the exponents of its prime factors.
Hold on, like if I had the state 12e, 12 is 2 squared times 3 to the power of 1, so 2 inner 3 the gills. Would it be linked to the exponents 2, 1 for primes 2 and 3?
Exactly. That's the mapping for the basis states.
Yeah.
Now, quantum superpositions, those complex states where a system is in multiple basis states at once.
The weird quantum stuff.
The weird quantum stuff, yeah. They're seen as existing within this prime logarithmic spectral space.
Okay, help me visualize this space. Is it like a graph or some kind of abstract map?
You could think of it like a unique coordinate system. Or maybe like an address book for quantum states, where the addresses aren't based on position or momentum, but on the fundamental prime factors and their weights, their exponents within the state.
So the address for 12A's is kind of like 2 for prime 2, 1 for prime 3, 0 for prime 5, etc.
That's the basic idea, yes. And crucially, in this SQM view, this underlying arithmetic structure isn't just a mathematical description. The paper argues it's what physically encodes the quantum information itself.
Wow. Okay, that's a big claim. So entanglement, that weird non-local connection, isn't just abstract correlation in this view.
According to SQM, no. It corresponds to a kind of harmonic alignment in the amplitudes associated with these prime addresses or modes in this special space.
Like two instruments are entangled if their overtones, their harmonics, based on primes, are perfectly aligned.
That's a helpful way to put it, yeah. And the paper even highlights that the fundamental theorem of arithmetic, the fact that every number has a unique prime factorization.
Yeah, learned that in school.
This serves as a bedrock principle for this arithmetic structure they see in quantum states. It's like the unique prime DNA for each basis state.
So the tuning fork analogy holds up. The fundamental tuning or DNA of a quantum state is set by the primes, and entanglement is when these prime-based tunings are in perfect harmony.
This arithmetic perspective is really key because it completely reframes the problem of decoherence and drift. Environmental noise doesn't just randomly perturb an abstract state. From this view, it causes a degradation or dissonance in this delicate prime-based harmony.
It knocks those arithmetic tuning forks out of alignment. And detecting that dissonance without touching the tuning forks, that's the challenge.
Right, because the standard projective measurement forces the system into a single classical outcome.
Which is like smashing the tuning fork to see what note it was playing.
Exactly. It destroys the harmony you were trying to check.
So how does this SQM perspective, seeing states through these arithmetic glasses, help you detect drift non-destructively?
Well, the paper looks for quantities that should remain constant if the arithmetic harmony is undisturbed, but which change if drift occurs. Things that are conserved.
Invariance?
Yes. They introduce what they call prime exponent operators, denoted as R. Think of these less as operators in the usual quantum mechanical sense, and more like special probes you could hypothetically use in this spectral space.
Okay.
Each R probe is designed to check for the strength or presence of a specific prime number PJ's signature in the state's arithmetic DNA.
So if my state's DNA involves, say, a factor of 7 believes, the R probe would somehow register that.
Precisely. And here's where the power comes in. According to the SQM framework and how they define the system's natural evolution, governed by something they call the Luizzo kernel operator, LKO, but the name isn't critical. This natural evolution preserves these prime signatures in a specific way. Because their dynamics commute or are compatible with these prime probes, certain combinations of these probes, which they term spectral arithmetic invariance, or IGMAs must stay constant, if the system is evolving ideally, without any external noise or drift.
So the invariants are the arithmetic fingerprints, the patterns that shouldn't change unless something goes wrong.
Exactly. If you check these specific arithmetic fingerprints, and they deviate from their expected value, it's a clear signal that the pristine arithmetic harmony has been disrupted. Drift has occurred.
Okay, that makes sense.
This is the core insight. You detect drift by observing changes in the fundamental arithmetic pattern, not by making a traditional state collapsing measurement.
It's like having a complex musical score, maybe. And instead of trying to listen to every single note at once, which, would just collapse the performance into silence in this analogy, you check if the underlying rhythmic patterns or the harmonic proportions are still correct.
That's a good way to think about it.
If those patterns are off, the performance has drifted, even without hearing every note.
That's the idea. And the paper points out you can design different invariants, like I1, which is sensitive to phase shifts in the arithmetic pattern, and I2, sensitive to amplitude changes. Different ways the harmony can go wrong.
Okay, so this theory about arithmetic fingerprints leads to a practical tool. The paper introduces a specific protocol called Spectral Constraint Violation via Ramsey protocol, or SCV-RP.
Right. This is their concrete method for putting the theory into practice. It cleverly adapts the familiar Ramsey interference concept.
Ramsey interference. That's usually used to measure tiny energy shifts, right? Like in atomic clocks.
Exactly. But here, they apply it to detecting changes in spectral coherence, essentially, whether that prime-based arithmetic harmony between entangled qubits is still intact.
So how does this protocol work in a quantum circuit? What are the steps?
Okay, first, they start with a standard entangled state. They use a Bell state, like 0-Pigemeller-2, which you can create easily with a Hadamard gate and a CNOT gate.
Okay, standard starting point for entanglement experiments. Got it.
Yes. Then, step 2, they deliberately introduce a controlled spectral drift. They do this by applying a simple phase gate, like an Arzel rotation gate, to one of the qubits only.
Just one of them.
Just one. The paper explains that within the SQM framework, this specific gate simulates introducing dissonance or a phase shift into that qubit's prime logarithmic coherence relative to its entangled partner.
So you're intentionally knocking just one of the entangled tuning forks slightly out of its arithmetic phase, like a controlled error.
Precisely, a controlled perturbation. Then, after this perturbation, they apply Hadamard gates again to both qubits.
Okay, what does that do here?
These Hadamards effectively project the system's spectral coherence information onto the standard computational basis, the 0 and 1 states, where you can perform a normal measurement.
Ah, okay, so you prep the entanglement, poke one qubit spectrally, then use Hadamards to translate that spectral information into something measurable.
You got it. And then step 4 is you measure the final state populations. You see how often you get 0, 0, 1A, 10A, and 11A.
And you pay special attention to.
You pay special attention to the leakage, the probability of finding the system in the off-diagonal states, which are 0, 1 air and 10A.
The states you shouldn't see if the initial Bell state harmony 0, 0 plus 7A was perfectly preserved.
Correct. The paper defines the drift probability, P drift, as simply the sum of the probabilities of finding the system in O1 air, or 10A, P01 plus P10.
And that leakage tells you something.
That leakage is the direct signature of spectral dephasing or dissonance. The clever part is, this measured leakage probability directly tells you about the deviation from those spectral invariants, the arithmetic fingerprints, without you ever having to measure those abstract invariants directly or collapsing the original entangled state you were checking on.
Whoa, okay, so you're doing a standard measurement at the end, but you're interpreting the results spectrally. It's like listening to the overall sound of an orchestra and noticing that because the harmony is off, energy is leaking into weird sounds or specific frequencies you wouldn't expect.
Yeah, that's a good analogy.
Rather than trying to measure the exact frequency of each individual violin directly.
Exactly. You're monitoring the effect of the lost harmony on the measurable output statistics.
Okay, that's the theoretical framework and the SCV-RP protocol. Sounds elegant, but... Did they actually test this? Does it work in the real, messy world? The source material includes results, right?
They did, both simulations and real hardware experiments. They first simulated the SCV-RP protocol circuit, just described.
Okay, the computer model first.
Yeah, right. The simulations, detailed in the paper, showed a really clear, predictable relationship. The drift probability, that P-drift leakage, it increased smoothly and sinusoidally as they increased the applied phase shift.
Sinusoidally, like a wave.
Yes, closely following the mathematical pattern sin. This confirmed that, in theory at least, spectral drift translates directly into the specific kind of population leakage. The simulations gave them an idealized baseline, free from real-world hardware imperfections and noise.
So the simulation basically said, if the SQM theory and the protocol are right, you should see this specific sin curve when you plot leakage versus the applied phase.
Precisely. Then came the crucial part, running the protocol on actual quantum computers. They used IBM's quantum processors, specifically in Brisbane and Imsterbrook.
Okay, the moment of truth. How did the real world compare to the clean simulation?
The results were quite remarkable, actually, especially on the Imsterbrook processor. It showed exceptional agreement with that predicted sin curve.
Really? How close?
Matching it within just a few % across a wide range of phase shifts. The measured drift probabilities spanned nearly the full theoretical range, from around 1% leakage for small phases up to about 98% leakage for a phase shift of breadth.
Wow, that's a really strong match. It means the protocol works pretty much as predicted, even with all the noise and imperfections of current quantum hardware.
It's a significant experimental validation, yeah.
Yeah.
It proved that you can indeed detect spectral coherence degradation, that loss of arithmetic harmony, without performing a destructive measurement on the entangled state itself. You just look at this pattern of population leakage.
And it demonstrates that current hardware, noisy as it is already capable of supporting this type of non-destructive monitoring. That feels important.
Very important. It's not just theory, it's practically achievable now.
Okay, so SCV-RP is a validated tool for non-destructive drift detection using the spectral arithmetic view. But the paper mentions a surprising discovery that came out of this work, something called Spectral Sympathetic Resonance, or SSR. What's that about?
Yes. This was an unexpected finding that emerged during their initial experiments with SCV-RP. They noticed subtle but persistent oscillations in the measurements that didn't seem to fit the standard noise models they were using. Something else was going on.
How is this SSR different from the SCV-RP protocol itself? Is it another tool?
No. The paper clarifies that SCV-RP is the protocol, the method, or the tool for checking drift. SSR is the phenomenon they observed, a coherent, oscillatory behavior, a kind of spectral ringing that appears to be rooted in the arithmetic structure of the qubits themselves.
Spectral ringing.
Yeah, and it seems to happen even in the presence of noise that should seemingly suppress such coherence according to standard models. It's like the system itself is ringing based on its prime tuning, its arithmetic DNA.
So the idea, the hypothesis, is that spectrally aligned qubits, based on their arithmetic DNA, can somehow resonate with each other when one is perturbed.
Kind of, yeah.
Not like a classical energy transfer, but something tied to this arithmetic alignment, this spectral property.
That's the hypothesis they explore. Does perturbing one part of this prime-based structure cause a resonant response in another? A response that reflects the underlying arithmetic geometry or symmetry. It's about resonance in this non-dynamical spectral domain.
Okay, that's a wild idea. And how did they test for this SSR phenomenon specifically?
They designed a modified experiment, also run on IBM Quantum. The circuit was slightly different from the SCV-RP protocol. A key change was adding a feedback loop CNOT gate after applying a phase shift to one qubit.
A feedback loop. Okay.
And the phase shift itself was specifically chosen to be related to the prime structure they use in RZ rotation, with an angle proportional to a times the logarithm of a prime number, like R's ln(p). Again, tying it back explicitly to the prime logarithmic idea.
So they apply a specific prime-weighted perturbation to one qubit, use a feedback loop, and then what do they measure?
They then measure the other qubit, but this time they measured it in the x-basis, which probes its phase coherence. They did this using an Y rotation followed by a standard z-basis measurement.
Okay, so the measurement is different too, focused on phase coherence of the other qubit. What happened?
Yes, and the results were quite striking, especially when compared to simulations. A simulation using Sherbrooke's standard noise model predicted a flat line.
Meaning
it expected complete decoherence. The noise model predicted that any phase coherence, any signal from this perturbation and feedback, should be completely washed out by the noise on the real hardware. It predicted basically zero effect.
Okay, so the simulator, designed to mimic real-world noise, predicted nothing interesting.
Exactly. But the actual hardware, it showed clear, albeit small, structured oscillations, the spectral ringing they were looking for.
Whoa, so the real machine did something the noise model said it shouldn't be able to do. It showed a persistent ringing pattern related to the arithmetic perturbation.
Precisely. The paper interprets this significant discrepancy as strong evidence that the real system exhibits coherent spectral dynamics, this sympathetic resonance that current noise models aren't capturing. It supports the idea that the arithmetic structure central to SQM isn't just a theoretical construct, but physically influences how these systems behave, maintaining a surprising degree of coherence in ways we don't fully model yet.
This feels like, well, maybe a potentially fundamental discovery. SCV-RP is a practical, experimentally proven tool derived from the spectral view.
Right, the diagnostic.
And SSR suggests this view reveals a deeper, inherent, resonant property of these quantum systems that we weren't accounting for. What are the big takeaways here for the future of quantum computing?
Well, as the paper discusses, SCV-RP gives us a reliable, spectral, non-destructive way to monitor for errors, which is huge. And SSR hints at a fundamental structured resonance that our existing models seem to miss.
It completely changes how we might think about quantum sensing, doesn't it? Entanglement might not be something you just check if it's there or gone.
Exactly.
It could be a continuous property you can actively monitor, like watching a subtle shift in the arithmetic harmony in real time.
Precisely. Decoherence could be viewed less as a sudden collapse and more as a gradual drift or dissonance in this spectral prime-based space. And it's something you could potentially track by monitoring effects like this leakage or maybe even this resonance.
This opens up a new operational window for quantum computing, as the paper puts it. That sounds promising.
It really does. Imagine.
Yeah.
Real-time tracking of entanglement degradation without interrupting your computation. Building feedback systems that automatically correct for spectral drift based on continuous monitoring.
Or maybe entirely new error correction schemes.
Possibly. Schemes that work by maintaining the specific spectral harmony or canceling out unwanted spectral ringing rather than just relying on redundant qubits and statistical measurements like current codes.
And the fact that a currently available processor like Sherbrooke demonstrated this capability, both the SCV-RP detection and hints of SSR, that's key.
Absolutely. It isn't just a neat physics experiment on exotic hardware. It suggests these ideas could be implemented and utilized in today's noisy quantum computers.
It's a powerful demonstration. The spectral perspective, SQM, it isn't necessarily replacing conventional quantum mechanics, right? It's more like a complementary lens.
That seems to be the argument, yes. A different way of looking at the same underlying reality. It suggests there's a layer of measureless insight available by looking at the state's inherent arithmetic structure. Insight tied directly to this prime logarithmic foundation that seems to enable both the non-destructive detection and perhaps this sympathetic resonance.
Okay, let's bring this deep dive towards a close then. We started with the fundamental problem, checking on fragile quantum harmony without shattering it.
The measurement problem for entanglement.
We explored source material that proposes looking at quantum states through the lens of arithmetic, seeing them connected intrinsically to the prime factors of numbers via this SQM framework.
We learned how this leads to the concept of spectral arithmetic invariants, like those arithmetic fingerprints that reveal drift when they change, conserved quantities in the spectral space.
And how this birthed the SCV-RP protocol, a clever method adapting Ramsey interference to essentially listen for that arithmetic dissonance through measurable population leakage.
A method convincingly validated by experiments on real quantum hardware, showing impressive agreement with theory.
And finally, we touched upon the surprising discovery of Spectral Sympathetic Resonance, SSR. This phenomenon suggesting these systems can ring according to their prime structure, even through noise, hinting at a deeper connection between number theory and quantum dynamics that we don't fully grasp yet.
Yeah, the resonance was really unexpected.
So the big takeaways for you listening. The SCV-RP protocol offers a validated, non-destructive way to monitor the health of entangled states right now. And the SSR discovery suggests a fundamental structure-based resonance might be at play in these systems, something beyond our current noise models.
It really solidifies this potential shift in perspective, thinking of quantum state assessment less like a destructive measurement that collapses possibilities.
The smash the tuning fork approach.
Right. And more like listening for the specific harmonies or dissonances inherent in the state's underlying arithmetic structure.
Which leaves you with a truly mind-bending thought to ponder. If the arithmetic structure of quantum states is this fundamental, if it encodes information, influences dynamics, enables non-destructive monitoring, and this strange spectral resonance, what other profound connections between the world of numbers, number theory, and the world of quantum physics are still out there just waiting to be discovered? Could harnessing this inherent arithmetic harmony, this spectral resonance, truly be the secret sauce we need to finally build stable, large-scale, fault-tolerant quantum computers?